All right, well, we'll see how we do. We may have to have Nick advance some for us if we don't get it going. But yeah, like Nick said, I'm Keanan. I run a company called Alpha Particle. We do digital consulting. And I'm here to talk about some computer science stuff. First of all, any like hardcore CS majors in the room? Okay, that's a little scary. You're both right up here. I'll try to do my best and not sweat through my shirt here. Places to find me online, this is Twitter and GitHub and everything else, and I'm also always on email, so if we pass the question and answer period and think of something 2 days from now you want to ask me, shoot me an email or whatever. Easy ways to find me. So, who am I and why should you care? Why did you invest your time tonight to come here? I was originally a self-taught developer. I wanted to build a website when I was in college. I'm not Mark Zuckerberg, but I had this idea and I wanted to do it, and I went to one of my friends and said, you know, you've done some computer science, like how much do you think it would cost to pay somebody to build this for us? He said, it can't be that hard, let's just build it ourselves. So we started, my first Google search was how to display a table of data in HTML, and I was off. Got about a year into the project and was doing some things that in hindsight, like definitely shouldn't have done. Our database was a text file with 250,000 lines in it that we searched through to find results. So if it had ever gone into production, I'm sure 3 people would have crashed it like instantly. Stuff like that, you know, PHP calling Python while it was running. And so it never really launched for reasons that weren't related to the tech stack. But I looked back at some of that and said, okay, yeah, I should like figure out how to do some of this stuff the right way. So I picked up a computer science minor, which is like the ultimate cheat sheet for me because I got all the foundational classes and then left before it got really hard. So that was awesome. But in a lot of cases, like I don't do hardcore computer science in my day job. So knowing the concepts is super helpful, but above that, it kind of wouldn't be as useful. So I view that as a win. And then I've been kind of, you know, picking up stuff on my own since then. So tonight we're going to go over some of the stuff that is foundational and helpful for even if you're not working for Google or whoever. So computer science concepts are cool. I think they're cool because they're really the underpinning of how everything works. Computers have been around for a long time, so we've developed a lot of abstraction layers on top of the core concepts. But you know, when you get that one weird bug that actually is a bug because of how computer science works underneath, it's helpful to know what is going on. They become even more important when your stuff runs at scale. So when you're dealing with a ton of requests or a ton of data or a ton of anything, you have to kind of make optimizations and things on your own that it's helpful to know what's going on so you can know what to optimize. Good background knowledge, like we said, when debugging code. The one example was I never really understood what a race condition was until I heard about it in my CS class. Basically what it is it's a process that's looking at a certain value, and that value is getting modified, and the other process doesn't know about it. That's kind of the simple explanation. So your code is getting really weird values for something that you think should be another thing. And they're kind of hard to pin down, especially when it doesn't get modified every time, or sometimes it gets modified later things. So, but knowing that that's a thing that you can look for if your code starts doing really weird things is helpful. And you can look really smart in front of your friends, which is what I hope I'll be doing over the next 45 minutes or so. Cool. So as I think Carl wrote in the meetup description, this talk is loosely based around these books right here. They're called the Impostors Handbook. And basically this guy Rob wrote these as a computer science primer for self-taught programmers, right? So the idea was if you've just been on Stack Overflow and learning how to code, you would really not have any occasion to pick up some of this stuff, but for all the reasons we've already outlined, it's helpful. So I picked up the first edition and have read the whole thing. I have my bootleg-ish copy. It comes as an ebook, but I really like printed things. So I took it to, actually you took it to Kinko's for me and got it printed. So if you want to like skim through it after, just come on up here and look through it. For the first edition, there's actually like a legitimate print edition now, so you can get it like professionally bound instead of Kinko's bound. And they just recently came out with what they're calling Season 2, which is just a whole other book. It delves more into the cryptography stuff and more kind of that side of things. So would definitely recommend if you like this talk, this is kind of just pulling a couple chapters out of here and going deeper into them. But these are great, and it's really well explained. There's awesome diagrams, some of which we'll see, so highly recommend. It's not my book. I'm not affiliated with it. I don't get commissions or anything, but I just really enjoy it. So what we're going to cover, despite the title, Computer Science in 60 Minutes, you're not getting a CS major when you walk out of here. We're going to just kind of pick and choose things that are you wouldn't necessarily find, just looking on Stack Overflow or things, but underpin a lot of what you probably do. and are helpful to know about. So the first thing we're going to talk about is a big O notation, it's called. Then we're going to look at a little bit of data structures, specifically stacks, just one specific kind of data structure. We're going to talk about how a computer understands the code that you give it, whether it compiles it or interprets it, and what that means. And we're going to look at public key cryptography, which is how computers communicate securely and things like that, which all of you have definitely encountered at some point. So let's get started. I hope there's no questions on that stuff before we start. Well, now I gave away part of the thing. That's not as exciting. Sorry. Having some clicker issues. All right. So the first concept is it's called big O notation. You've probably seen this sort of syntax maybe in some super complicated Stack Overflow answer that you just close because you don't understand. But essentially it boils down to a measure of how efficient is your code, or how well is a certain algorithm that you have running. So it's typically notated like this. And this is one of the answers to how efficient is your code. This denotes that your code is running in constant time. So basically, big O notation takes a look at when you run your code and you give it a certain number of inputs, how efficiently does it run compared to if it had twice as many inputs or 10 times as many inputs or whatever. So if a piece of code runs in constant time, or in this case O of 1 as you could pronounce it, that means no matter how many inputs you give your code, it's going to take the same amount of time to run. So I'm not a super picky shopper. So when I go to the grocery store, I shop in pretty much constant time because I see the item on my list, I go see all the ketchup, and I pick the first one I see. If there's twice as many ketchup bottles, like I'll still pick the first one I see. It will still take me the exact same amount of time to shop for ketchup. It's not an issue. That's just me. Don't judge me. So for me, like picking ketchup off the shelf is a constant time algorithm because I just take the first one that I see, no matter how they're ordered, no matter how many there are. That's just what it is. So the next kind of complicated option up is what's called linear time, which is O of n. So n is the number of elements you're passing to your function. And this means that if you give it more inputs, the time it takes to run will grow linearly. So if you give it 2 times as many inputs, it'll take 2 times as long to run. So for example, this is the spoilers you already saw earlier. I have a cat at home. His name is Meowin' Brando. And he loves to hide around the house. He has a bunch of different places where he hides. Some of them are very obvious. So he sometimes sabotages my code. He sometimes just sits directly on top of me. But some of them are not so obvious. He hides under the bed. He hides on these shelves we got him. He hides on top of the fridge. A bunch of different places. So when I get home, if I don't see him, I kind of just wander around, like trying to figure out where he is to make sure he didn't get out or whatever. I'm very paranoid in that way. So that exercise, checking all the places where I know he hangs out, is linear time. So if I built him another spot to hang out, that would be another place that I would potentially have to check. So when we're talking about how to determine the O notation, we're talking about kind of the worst case scenario. So it's like, yes, finding him could be constant time if he's sitting directly on top of me, or if I can see him when I walk in the door, right? That's constant time. But potentially, he could be in the very last place I check. So if I add another place, he could then be in that very last place I check. So the time it takes to run this algorithm of finding him around the house scales with the number of hiding places that he has. Does that make sense? Cool. And also, I get a chance to show off cat pictures, which is awesome. So kind of the next level up is O of n squared. This is where it starts to get bad. So you can kind of see the goal is to make your code run as fast as possible, as efficiently as possible, right? So as we get these bigger values of n, now our time is going to increase not linearly, but even more than that. So as we add more and more data to this sort of stuff, the execution time is going to go way up. So this is a problem. For example, if you were running a search engine for 10 web pages, maybe you don't care about this because it's fine, but as soon as you get to Google scale, you don't want each additional web page you add to increase the time to run by a lot. That'd be bad. So the most common case where you see this complexity is with nested for loops and things that are usually considered code smells or stuff that you want to refactor because it's not good. Here's an example. This is not super readable. But basically, we set off our value n to be 1,000, and then we have a for loop that loops through, echoes out the values of x, and inside that we have another for loop that echoes out the value of y, right? So if I double n from 1,000 to 2,000, this is going to take more than twice as long to run because it has to go through each for loop twice, right? So again, this is a trivial example that doesn't really do anything useful, but if you have a data structure that requires you to loop twice through the data you're looking at, that's a problem. And that's where you get into this increased complexity. Okay, cool. So then this, you can see we kind of flipped it, but it's actually even worse at this point. An example of this sort of algorithm is if you recursively calculate Fibonacci numbers. Each next number you add will increase the complexity by a lot if you have to go back and calculate all the ones before. And this is not great, again, especially with a huge data set, because, like we said, each number you add will then increase your complexity by a lot. So ways to get around this, if you have to use this sort of algorithm, are to either cache some values or cache the final results of your, and then not have to calculate it every time, or cache subparts that you've calculated and then just mash them all together in something that can be closer to constant time. So in our Fibonacci example, if you knew you calculated from 1 to 5, and then you had 1 to 6, you could say, well, 1 to 6 is just 1 to 5, then plus 6. And if you already had that result pre-calculated, you would get it much closer to constant time. So things like that, you can get around it. Or if you're like me, when I wrote an algorithm for myself that was taking way too long, just put it on a huge AWS server and run it for 5 minutes and then only pay for that. But that's not a great plan, especially when you need to actually run it as your whole day job. Cool. Yeah, this is also an option, but this is just a function that will never finish, so probably not a great thing to write and or run. But for consistency's sake, we'll cover it. Cool, so let's talk about how this actually works, because we've looked at some pretty trivial examples so far, and nothing that really you can kind of sink your teeth into. So let's think about this in an applied example. So our example is going to be, I want to look somebody up in the phone book. So I have a phone book. Yes, they still exist, I'm told. I saw one at McCormick Place the other day in the payphone area that was dusty and crazy. But I want to find somebody in the phone book, and so all I have is their name, and I want to look up their phone number. So I know that they are somewhere in there. My first kind of crack at this would be just, oh yeah, loop through every person in the phone book and check, does this name match the person I'm looking for? If yes, I've found their phone number. If not, I need to go to the next person. So this is where it comes time for audience participation. Given all of the possibilities we just looked at, what is the complexity of this algorithm, looping through every item in the phone book and trying to find the person that we're looking for? Anybody brave enough to take it on? Yeah.
Isn't it just 01?
It's, what is it, 01?
Yeah, or big O notation 1.
Sure. So 01, why is it 01?
Because it's just a simple list of like names, and you imagine it with the value you want. It's not complex.
Okay. So his answer is it's O of 1 because it's a simple list of names. It's not complex. I'm just doing a matching. That's actually not it. So if you think about it, what would happen if I added one more person to the phone book? I would potentially have to check that last person to see if it's the person that I'm looking for. So this is actually, it scales linearly with the number of people in the phone book. So that's not bad. The only example we looked at that was better than that was constant time. But you know, if I have millions of people in the phone book, or this is a database of everybody in the world, I would love to have something slightly better than this. Because again, the goal is always to get as close to constant time as possible. So let's think about a different way we could sort the phone book. Oh, well, I already gave away the answer to this question. Yes, there is a much better way to do this. And the reason that there is a better way to do this is because, now there's the answer, the phone book is already a sorted list. So if you imagine I'm holding the phone book in my hands, and I rip the phone book in half. In constant time, I can determine which half of the phone book the person I'm looking for is in, because the phone book's alphabetized. So that's an easy check. And so what we could do is take the half of the phone book that the person is in, throw out the other half, and now we know they're in here. We've already eliminated half the results. We don't have to go through those. And if I take the section that I have and rip it in half again, and I, again, in constant time, know which section that the person is in, throw out the half they're not in, and keep going, eventually I'll get to 2 people, and I can just check, is it the first person? And if it's not, then it's the second person. And so then we've looked them up and we found their phone number. So that's great. We don't have to search the entire thing. We eliminate half the results every time, which is awesome. And the reason we can do this is because it's sorted. If you just had a random collection of people, you couldn't do this because you didn't know whether the person you're looking for is in the first half or the second half. So for those of you who didn't see the answer already pop up on the screen with my clicker malfunction, this is obviously better than linear, but is it constant time? No, it's not constant time, but it's close. So this is kind of a trick question because we didn't cover this one, but it's O log n, which is, like we said, not quite as good as constant time, but better than linear time. So for each person you add, if you add twice as many people, it's not going to take quite twice as long, which is good. So we've improved that a little bit. And that's where, when you start to think about, you have 3 different ways you could tackle a problem. This is sort of a framework for figuring out which one is the best way. It doesn't take into account other real-world constraints you might have, but it's a start for sure. Yes. So again, this is like probably a solution. Ripping the phone book in half is probably a solution I wouldn't have thought of if I had not been exposed to this sort of stuff and kind of thought about it in a different way. So this is a good example of why this is good background information to have in your pocket. Cool. So questions about that stuff before we move on to something completely different? Yeah?
I haven't seen the phone book.
Okay.
Do they still like send them to people's doorsteps?
I guess. Yeah, I mean, I don't personally get one, but I think my parents get one, so maybe it's a suburbs thing. I'm not sure. But yeah, so useful for this example, though. I can't off the top of my head think of a digital equivalent that would work that way. But yeah, it's because it's a sorted collection that we can do the whole ripping in half thing. Also because it's a physical thing, it's easier to envision ripping it in half. Dictionary could work. Yep. I know those are still around for sure. Cool. All right, well, let's keep going. So we said we were going to look at data structures a little bit. Data structures are just the idea that when you have a collection of data, you can store it in many different ways. You can store it sorted, like a phone book. You can store it in something like a database where you have keys that you can access it from and stuff like that. But we're going to look at a specific set of data, specific type of data structure called a stack. And the reason we chose a stack as opposed to any of the other ones I could have picked was because this is the one that I think y'all are most likely to have encountered, even if you don't know it. And it's also relatively easy to visualize. So stacks are a data structure. You can only really do 2 things. You can push something onto the stack, or you can pop it off the stack, right? You can think of a tower of blocks or a stack of books or whatever you want to visualize this, but that's the basic idea. They're known as a last in, first out data structure, which makes sense because the last thing you put in, if all you can do is pop off the stack, that has to be the first thing you take out. A true stack, you can't search into the middle and grab something because then the whole thing would collapse. And I would argue the most common use case for these are function calls. So we're going to take a look at an example. Again, sorry, it's a little bit hard to read. All the rest of my stuff's high contrast, but not my cool-looking code examples. So we've got these 3 functions, and what we're going to do is just call ABC. So when we call a function, PHP in this case, I guess, talks to the computer, says, hey, computer, I'm going to run some functions. I need some space. I need some space to make a stack. And the computer says, all right, we've got some memory lying around. Here's some space for your stack. And so PHP says, all right, ABC is what I'm calling first. So it puts ABC in the first position on the stack. We go into ABC, and it starts executing. It says, all right, result, we're going to set that to the return value of DEF, and then we're going to echo it out. OK, cool. DEF, though, is a function. So let me go see what that is. And it's going to call DEF and put DEF on top of ABC in the stack, because that's the function that needs to execute. So it's cool, DEF. All right, well, I'm going to return the value that comes from XYZ. All right, XYZ is a function, so let me go there. So it puts XYZ on top of the stack there, and then says, all right, well, XYZ returns a string. This is the result. Cool. So then XYZ is done executing. It pops it off the stack and passes the result back to whatever's below it, which is DEF. And DEF says, OK, cool. I don't need to do anything with this. I'm just going to pass it back to whatever called me. So it pops DEF off the stack and returns that value to ABC. So now the string has gone all the way back up to ABC, where it sets it into the variable and then echoes it out. And then ABC is done executing, so it pops that off the stack, and that stack's empty. And then PHP says, all right, you can have your memory back. I'm done. So that's a very basic concept of how functions can get kind of stacked up on top of each other. So really the only time that this kind of behavior is exposed to the user or to you, the developer, is when function calls go bad for one reason or another. So I'm sure a bunch of people have seen this sort of thing. If not, you're a much better programmer than I am. And you see here, it's telling you what the call stack is. And if you've never understood why it's called a call stack, it's because it's exactly what I just described. All these functions are stacking up on top of each other because they call each other. And they all rely on the result of the thing that's on the very top of the stack, and then they all just pop all the way back down. So it's telling you, hey, here's the stuff that's currently stacked up at the time when this error got thrown. So if it's not the code that you wrote, it's something somewhere else down this stack that's throwing an error. So you can kind of go start to investigate that there. So it's just super helpful to kind of visualize what's actually going on in your application. Again, you don't love seeing this screen because it means you did something wrong, but if you understand that, okay, here's what I'm looking at, it's actually just a stack of functions that have all called each other all the way down, and then if my stuff was running correctly, they would all pop and go all the way back up. But for one reason or another, in this case, it's an unexpected semicolon, they're not functioning properly. The second case where you might have seen this, and this is just a cool piece of trivia you can take away from this presentation. I'm assuming everyone has been on Stack Overflow at least once, okay? For me, it's like 40 times today. So, but I always thought it was kind of a weird name. Like I never really understood what was going on. So what is the Stack Overflow? So before we talked about how when a program says, I'm going to need to run some functions, give me some space for the stack. The computer says, all right, here's how much space you get. And you can put stuff on the stack as much as you want, as long as it can all fit within this space in the memory. So Stack Overflow occurs when you try to push a function onto the stack or any sort of data item. In this case, we're still talking about functions that makes the stack bigger than the space that's been allocated for it. So in this case here, we see a fatal error. It says maximum function level, nesting level of 100 is reached. So in this case, the system stopped us from stacking too many functions on because it enforces a hard limit of how many functions we can call inside each other. If you don't have this hard limit, you'll encounter code that just runs forever because it just keeps calling itself or calls other things that like calls each other and all this sort of stuff. And eventually, yeah, your system will fail because your stack will get way too big and it won't be able to handle it. This is also not as much anymore, but this a while ago was frequently exploited as malware. So like we said, the stack is given a certain address in memory, a certain location where it is. And if you can overflow the stack, you used to be able to break out of the memory that the computer assigned to you and access stuff that was in other memory locations. So data from other applications or system information or things like that. Overall, bad news and led to unexpected consequences. So little trivia, little data structures. Cool mix. Questions about stacks? Yes?
That 100 like function call limit, I know PHP has that as like one of the INI6, right?
Mm-hmm.
So does that count including like recursive functions, or can you do recursive?
Yeah, so like for example, with that, you couldn't, if you wrote a recursive Fibonacci algorithm, you couldn't count Fibonacci 101 because that would be over the limit of the stack. So that's the same thing. It's in place for your protection, whether you're being intentional about it or not. And if you know you are being intentional about it, then you can raise that limit on your own, but it's there to prevent stack overflows. The bad kind, not the helpful coding kind. Yeah, good question though. Cool. All right. Does anybody know what time it is? I should have brought my watch up here.
7:19.
Oh, wow, okay. We're flying. All right, then we're going to talk about how does a computer know what to do? That's a very existential question, so we're going to break it down a little bit. Who here does a lot of their work in a compiled language? This is maybe a trick question, depending on who we're talking about. But some examples of those are these. So obviously there's way more than this. These are the ones that I thought people would know and recognize and have some experience with. But most of the rest, this is my favorite XKCD comic. We'll talk a little bit more about this, but basically a compiled language means that when you write some code, you have to tell the computer like, all right, I'm done, I want to run this. And it says, okay, let me think about it for a little bit, and then gives you back a file that you can actually run. You can't just run the source code as you hit save in your text editor and then run it. It has to do some work. And depending on how big your project is or how many changes you're making, this can take sometimes a long time, so it has become a popular excuse for programmers to slack off. And that's the gist of this. But anyway, XKCD is always good to include. Oh. Did you guys get all that? That was the right speed of the presentation. So the rest of the languages that we didn't talk about are what are known as interpreted languages, which follow a lot of the same process, but they just happen at runtime. So they happen when you load a page in your browser, or when the server gets a request for an API endpoint, or when you just run a Python script on your machine, like stuff like that. That stuff all happens at runtime. So compiled versus interpreted, both pretty much work. When the computer is understanding your code, they both work in a similar way. It's more of just when that understanding happens. So PHP is a mix of both. It's mostly interpreted, but a lot of stuff happens at runtime, but it has certain things that help it run faster and make kind of pre-calculations. And if you want to know more about that, there's probably PHP internals people around here somewhere that you should ask, because that's a cool thing to get into. So now let's talk about what does a compiler or a computer actually do when you give it code. Again, like we said, this process is the same for compilers and interpreters for the most part, but it's just when it happens. So we're going to talk about compilers right now, and there's going to be a lot of like big technical words in here, but we'll use examples, I promise, because this is not a thesaurus or a dictionary. So step one, lexical analysis. Some of you probably know what that means. I didn't, so I had to look it up. And basically what it does is it takes the code that it's given and splits it into what's called tokens. So a token is like the smallest unit that a compiler or an interpreter can understand. So this could be a string, or a left curly brace, or an open quote, or a semicolon, or a comma. And it labels them based on what it finds. So here's an example. This is actually a diagram from the Impostors Handbook. We've got a simple statement up here: if x equals 10, console log hello. This is actually JavaScript, but close enough. So we'll be good. So here's how it kind of breaks it down. It says, okay, we've got an if. Oh, I got one of these, don't I? We've got an if keyword here, and that's going to kind of kick off our whole statement. We've got these separators, so our symbols are open parenthesis, our close parenthesis, our open curly brace, another open parenthesis, close curly brace. We've got a string here because it's enclosed in quotes. We've got a number, and we've got some white space. So this is obviously, there's also white space here. It classifies all of that. It classifies the entire piece of code that you've given it, and it says, okay, now I have a structured representation of what this code is, because I know what type of thing it is and what the actual value is. So I have a keyword that's if. I have white space, I have a separator, and all that stuff. So once it's broken down into there, it starts to actually parse it. So it says, okay, I've got this if statement here, and then it's followed by stuff in parentheses. So I know that's a relationship. And because it's right after this keyword, I know it's the predicate. So it's the beginning of a conditional. And then here I've got this function call, and then it passes a string in there. And because it's after this predicate part, we know it's a then statement. So it says, okay, yeah, I know this is an if-then statement. So once it knows it's an if-then statement, it can then make further decisions and things about how it's going to actually handle that, where it puts this code in memory and things like that. So now that it knows what it's looking at, it tries to figure out what you're trying to do. So this is things like, okay, they're setting this variable here, but they already had it set up here. Should I reset it? Is it in scope? Where should this variable be available otherwise? Will this branch of code, ever even be reached? Is it an if-then that will never succeed? Stuff like that. And when the computer kind of guesses wrong, like this is where weird errors start popping up. And this is, again, one of those things where if you just see like your code like running and producing weird output that you didn't expect, this is not maybe one of the things you think of, but it sometimes is the case. So for an awesome example of this, I didn't include it in the talk, but Gary Bernhardt does an awesome talk called WAT. It's, I think, 4.5 minutes, so it's a really quick watch. But it's like feeding weird combinations of strings and things to Ruby and JavaScript and seeing really bizarre outputs. And that's at the core because JavaScript says, okay, like empty array plus empty array, I don't know what you want me to do with that, so I'm going to guess. And then if you give me like empty array plus empty object, I'm going to guess. And then you do object, you flip it and do object plus empty array, and it gives you guesses different. So highly recommend it. It's less than 5 minutes. And if you want to watch it after this, we'll put it on or something. But that's an example of when an interpreter or a compiler guesses and either doesn't guess consistently or guesses incorrectly from what you were meaning to have it do. And then the last piece is optimization. Most languages try and help you out based on what they guessed you were trying to do. So you've seen some of this if you've ever minify your code and you see all the variable names get shortened to like 1 or 2 letters because that's more efficient to run. It does things like swapping data structures and swapping statements and things to make your code more efficient without you having to do anything. So I don't super know the details about this, but like when PHP 7 came out and stuff was running twice as fast as PHP 5.6, people weren't changing their code around. That was just the language helping them out. And some languages are better than others, and some languages optimize differently than others. So this is, again, if it's a useful case to know how the language you're using does it and what it optimizes for versus other possibilities, because that can come into play if you're running this a lot. So we already talked about this a little bit, but interpreted languages do this too. They just do it at runtime. So it's the same process. They parse code in the same way and make the same choices. Cool. Question about that? Yes?
I never experienced transpiling, like it's done for JavaScript from one ES level to another.
Yep.
Versus compiling. Is there a difference in just like?
So the question was, what's the difference between transpiling from like ES6 back into older JavaScript versus compiling? So compiling is basically turning the code that you're running into machine code. So it's making it accessible to like the lower level stuff on a computer. From what I know, transpiling is just converting it. Yes, it's converting it into something the browser can understand, but it's still the same basic form. It's not really changing it all that much in terms of it's still JavaScript, and it's not converting it from like C++ to machine code. It's JavaScript to JavaScript.
Like if my transpiler takes my JavaScript and turns it into WebAssembly, is that actually compiling, or is it still transpiling? Like, is it fuzzy? Is it not?
Yeah, my answer, the question was, where do you draw the line? Like if JavaScript is JavaScript to WebAssembly compiling or transpiling? I don't know, maybe. I don't know a lot about WebAssembly, but that seems like it lives close enough to machine code that you might be able to call that compiling. I also think transpiling is a relatively new term, so I'm not sure where that line exists, but that would be an interesting question.
Compiling comes out of computer science. Transpiling is people writing JavaScript scripts that just came up with a new word.
Well, there you go. That's kind of what I thought, but yeah. So sorry, what? Oh yeah, so he said compiling comes from like historically computer science when like most languages were written that way, and transpiling is just JavaScript people talking about JavaScript. That's not a super technical definition, but yeah, I think that's pretty much where the line is that's kind of where it originated and started. So yeah, good question though. Yes, in the back.
So you said that you should kind of give an idea of how the language changes things from just variables. Is that in the docs usually? I mean, do you go on PHP.net and see where that happens?
Yeah, I mean, so for stuff like PHP that lives, very online, like I would think that that would be in there. And mostly I think that would be in there in cases where people ran into weird bugs. And internals people came in and said, oh yeah, this is why this is happening because we're making this substitution or doing this kind of change invisibly, that you don't see because you're not looking into the compiler. But yeah, I think a lot of that stuff is documented in the docs, but I think some places host it kind of separately than like the developer docs. It's like internals docs for people. But yeah, I would definitely look there first, especially if you're struggling with a specific problem where you want to find a language that does something a certain way. The other alternative is to post very confidently the wrong answer and wait for people to pile on and tell you why you're wrong, and then that's another form of finding that information out as well.
I think it would be interesting to see, at least for me, to see 5.6 versus 7 and how things change.
Yeah, so 5.6 to 7 in PHP, like there's lots of like articles and stuff written about that specifically. So yeah, just like toss that into Google and there's lots of good documentation there. Not even like dev docs, but like people dug into it and wrote like human readable blog posts about kind of what stuff changed and how they were able to make it so much more efficient. Cool. Yeah. Yes. Back? Yeah, sure. This one? So like we talked about when we were talking about data structures, like for certain operations, some data structures are more efficient than others. So just like how when I built my first website, I was storing all my information in one big file, whereas a database would have been better. That's an extreme example, but if you want to store something in an object instead of an array or things like that, if the programming language can make those substitutions for you, it might make your data quicker to access or make your code just run better if it has enough information to confidently swap stuff around like that. Does that make sense? Sometimes, yeah. And again, it's language dependent in a lot of ways, but if a language says, hey, this is something I'm really good at, I'm going to do it this way, even though you didn't write it this way, that does sometimes happen. And that happens more frequently, I would say, with modern languages as opposed to like C++, where you have to like dictate a lot of stuff yourself. But yeah, in a lot of cases, they'll try to help you out like that. Cool. Yeah.
Would it be correct to assume that compiled languages are typically faster at runtime because they're not doing, actually running?
Yeah, that's the theory, and I'm pretty sure that holds true for all of compiled languages. Just because, yeah, like a lot of the work's already done. It's like pre-rendering of a feature-length 3D film versus playing a video game. Like the video game, the stuff has to happen live, whereas the film you can do all the work ahead of time and then it just plays back really smoothly. But yeah, so that's generally the rule. Did you have something to add about that?
For the language running itself, but if your program is doing mostly I/O, then any program spends.
Yeah, that is true. So yeah, so if you're writing a program kind of in a vacuum that just has to run, if you say parse this 10,000 row table, not even a table because that's I/O as well, but yeah, if you're depending on input output or network latency or whatever, like then you're at the mercy of whatever your slowest input is. But if you're talking about two programs that run in a vacuum, the compiled one will run faster. Cool. So this is kind of an endless like flame war, compiled versus interpreted, like which language is best, blah, blah, blah. So don't get sucked in too deep with it, and we're not going to either. So we're going to move on. And this is kind of the last thing that was super interesting to me when I started thinking about it. I never really thought about this as a hard problem. So public key cryptography, basically the idea of how can you exchange information, authentication, things like that, securely on the internet with someone you've never met or you've never had a history with, right? So if I say, I'm thinking of a number, and then I have Bryce, who I have a history with, think of a number, and then I say out loud, the number that I'm thinking of was the code name for the last project we worked on together. We're both going to say 43, and none of you, you maybe could have guessed it, I suppose, but you wouldn't have any way to verify that that's the number we were both thinking of. That was an encoded message. The only reason we were able to do that is because we have that shared history. We already had kind of the encryption key that we both knew. So that was like this slide and this slide. But it would be much harder for me to do that with someone I'd never met. I could, maybe try and come up with something that we both knew about that plausibly none of you knew about, but it wouldn't be as sure of a thing. It would probably be something that someone could just look up on Google and figure out the encryption key that we use, things like that. So that becomes a much harder problem. So passwords are great for encrypting stuff. If you give the person you're trying to talk with the same password, they can use that to decrypt what you've encrypted. But then the issue becomes, if this is a person not sitting across the table from you, if it's someone halfway across the world or somewhere else, how do you get the password to them initially in a secure way? Yes, you can send it an email, but then the NSA has it. You could call them on the phone and read it to them over the phone, but then again, the NSA has it. You could put it in your briefcase and fly to London and take it to them in person, but then you run into Jason Bourne and now he has it. So passwords can be intercepted. Like encryption keys, if both people have to have the same key, there's still the problem of communicating the key in the first place. So this is where we're going to just generate 2 instead of 1, because that's obviously better. This leads us to a concept called asymmetric cryptography, which means each side of the exchange has different information. And this is great because it means we don't have to exchange all of the information needed to encrypt the data, which means we can keep some of it secret, which means Jason Bourne can't get it. So how this works is you've seen this on your computer, I'm sure. If you've ever tried to connect to any service that requires keys, you generate a public and a private key. Your public key, you could publish wherever you want. You could give it out on your business card. Cool. Your private key, you definitely don't want getting out, because if it's out, then everyone's got everything. The combination of these can be used to authenticate a user or encrypt messages and data in a way that you never have to share your private key with the person you're trying to communicate with. So how does this work? We're going to talk about a real quick demo. If you've ever used SSH to connect to a server and used a key instead of a password, which y'all should be doing. This is, something everyone's experienced pretty much, SSH stuff. OK, cool. So for those of you who haven't, SSH is basically you're logging into another computer from yours so you can run commands and make it do things and all that stuff. So how this works is we have a client and a server. The client we're going to have as my nice computer icon here, and the server is going to be what I'm trying to log into. So let's say I want to make updates to my website or whatever. I need to log into the server to do that. So on the server, I've already given it my public key. Whoever runs the server has put it on there and says, yeah, this person with this public key is cool to access this server. But if you remember, I said you could print your public key on your business card. So that's not enough information, because if I gave my business cards out, like y'all could just go into my website server and use the same public key and be like, oh yeah, I'm good. So actually what happens is kind of a complex, we'll call it a handshake, I suppose. So when I hit a server, my computer says, hey, I want to connect. Here's my public key. And like I said, the person who runs the server has already added that there. So the server knows who I am when it sees my public key and says, oh, yep, OK, cool. Like, I see you here in the list of people who you're on the list. So here's a number that I encrypted with your public key. Like, just take this. And I was like, all right, cool. I'm going to go do some work with this. You do some work with this server on your own, and like we'll come back in a little bit and see what we both got for the answer. So I use my private key now, the one that I haven't shared, to decrypt what they sent me, because that's how private and public keys work together. The private key can decrypt the public key, whatever was encrypted with the public key, but not vice versa. That's what keeps it secure.
So the public key can encrypt but not decrypt 2% one way.
Yeah. So, and then I take that number that I decrypted and pull it together with a bunch of other session data that I know about my connection and stuff I'm trying to do. And then I say, like, all right, like, here's what I got, server. Like, what did you get? Because the server also did all of this same computation on its side. And so if our numbers match, then it's like, yeah, all right, cool. Like, you're in. Let's do this. Update your website. So that's, again, like a lot of simplification there. But the basic idea is that you can now authenticate with stuff like that without having to rely on the one password that will expose all your communications. The combination of the public key and the private key and how they're mathematically related makes the whole process secure. Cool. So again, asymmetric because we have our private key, the server doesn't, and the server has its own information that we don't have. So the information is not symmetrical. And they use the shared key, which is the public key, combined with their secret information that each side has to authenticate and see if they get the same answer. And if they do, then the connection is secure. Cool. That was a lot. So again, like, this is not a CS major. We just kind of scratched the surface. I chose kind of randomly, like not randomly, but topics that I thought would be applicable. But it's by no means a comprehensive review of computer science. So if this sort of stuff interests you, definitely look at these two. There's also courses and a bunch of other awesome free content on the internet for people who are interested in this. And just kind of start exploring and like you'll start seeing the connections from what you're learning to stuff that you've done, or, oh, that reminds me of code that I wrote 6 months ago, or things like that. And it's really kind of cool to feel like you're picking up more knowledge, but not just like random knowledge that's actually applicable to you. So again, here's how to find me online. We have some time for questions, if there's anything. Yeah?
Going back to the data notation example, if you had a dictionary like with a table of the first letter, and you were looking back instead of like throwing out half the dictionary,
Sure.
how would that change the website?
So the question was talking about big O notation again. If you have a table that tells you you're saying like, if you have a dictionary and you say, okay, the words with the letter A are on page like 1 to 50, is that what you're talking about? So yeah, so instead of ripping up half the book and throwing it away, you could immediately narrow your search to the 50 pages that your word is in, because you can compare the first letters. Yeah, I mean that'll make it more efficient. Once you narrow it to those 50 pages, you still have to do either a looping search or some other sort of search to get. It seems like it would be faster than log time, but I would have to think about that a little bit. Yeah, that is a similar way to kind of how hash tables work. So again, this is a case where like different data structures or having your data organized in a different way can give you efficiencies in your code, and that's one example. I don't know the O complexity of hash tables, but it's better.
We care about the big factor, not so much the constants. But then you set it up by 8 times. That's a constant, and it's still the overarching. What's the big biggest factor? It's the biggest volume that we care about. So I think it still would be.
So that would be what you're saying is that it would still be because once you got down to the 50 pages that had the letter A, you'd still have to search through those. Yes. Yeah, if you didn't have a way of optimizing that, then yeah, you'd have to look at that before. Yeah, that's a good point. Before it changes your.
So we care that it's n squared, but we don't care it's 4 times n squared.
Cool. Yeah, that was a good question. And yeah, so like that's the kind of stuff where like learning about data structures for data structure's sake is kind of in my mind tedious, but if you have a specific problem that like you're trying to solve, it's cool to see that, oh yeah, someone's already thought about this, and like doing it this way will give me a huge amount of efficiency gain as opposed to just how I was going to try it on my own. Cool. Yeah.
Big O notation strikes me as kind of like at the terror level, like it's brown or it's red. It's something that's talked about where you look at that and you look at a function, for instance, and you could say, oh yeah, that's O. How in actual practice, how is big O notation used? Can you actually calculate that, or is it just used as sort of that guide?
I mean, so you can, like you definitely can. If you're looking at like algorithms that are more complex than the ones that we were looking at as sample, you kind of have to break it down into pieces and like he was saying, like calculate which piece is going to actually be your bottleneck, and that's kind of where you look. But really, I mean, the way that I've used it, besides answering test questions when I was in school, is just thinking about like, okay, here's kind of my baseline. And when I was searching through the dictionary, like my baseline was O of n, so linear. Like, is that really the best that I can do, or could we think about a way to get this like another level more efficient? So it's not, I mean, I'm sure somebody somewhere is making all their devs like comment on tickets with the big O notation of their functions that they're writing, but I think it's more of just, at least for me, like a guideline of, okay, here's what I'm doing. Is this complexity what I would expect for how complex of a thing I'm trying to do? Or is it like I'm trying to do a lookup and it's like, it's going to be O of n squared. Like, if it is, I've probably got too many loops somewhere, I could do something more efficiently. So it's kind of just like a check for me to make sure I'm not writing like really bad code outside of the realm of like what could be possible. Yeah. Cool, yeah.
I just wanted to add a little bit more to that. And that, like, at least as far as I've used it and seen it used, it's always been as like a rough measure of where performance is, because computers under the hood and operating systems and everything, there's so many layers of caches and optimizations everywhere that big O is not going to tell you how much faster this is than something else is. It's just a very rough measure as to like how slow it can be when you have this many inputs.
Yeah, that's a good way to put it. Cool. All right, well, thanks y'all for having me. We still got some time to hang out and kind of meet and mingle and all that stuff. If you want to check out the Impostors Handbook, like I said, I got the copy up here. You can come look at and flip through. But otherwise, thanks so much.